In this video, we're going to look at the Laplace transform of whole differential equations and see how this ties into the representations we've been using so far in Python. If you look online, it's easy to find tables of Laplace transforms. I've included some key ingredients here that are typical in the kinds of functions you'll run across in mechanical applications. And what we see is that we have the definition, and we also, fortunately, rarely ever have to use that definition in practice. So just keep in mind that this integral is a lovely thing. It ties back to the Fourier transform in a whole host of interesting mathematical ways, but day to day you don't actually use it. What you do use are these table entries here, which have pre-calculated this transform value for you. So for example, functions that you see fairly regularly are constant functions, and those give you a 1 over s value. And if we go down the list, we see exponentials, and they transform to these forms here. And other kinds of functions that we encounter regularly in our solutions are cosine sine functions. So those are all in there, and they have relatively simple representations. For now, it's just enough to recognize that if we start with a function like an exponential, we get what looks like a polynomial, actually a rational function here as the transform version, and the same thing for cosine sine. What we're going to use more of for this video, though, are the transformations of the derivatives. So the idea is that if we know that we have a function that's in the time domain, and we take the Laplace transform of that, it's going to get converted into some new function, just like these functions here are. The only difference is we don't actually know what that function might be, so we have to solve for it as we go forward. The convenient thing for differential equations is that if we don't have the function itself but its derivative, well, it turns out the transform is simply s times the original function, and then there's some additional term that relates back to the initial conditions. And likewise, if we have second derivatives, we get two s's, or we get an s squared, and then we have functions or values that depend only on the initial conditions here, initial position and velocity if it's the second derivative. We're going to use these three transforms here, well really these two transforms, first and second derivatives, to analyze and convert the differential equation for a couple of the systems we've seen already, and just see how this plays out. So again, u is a function of time, and it is our control, and we want to be able to see how, if we have a natural cooling system, which would be this portion of the differential equation, my rate of temperature change is equal to negative k times the current temperature. We want to see how that gets influenced or affected by having a control added, and we're going to see how that plays out with the Laplace transform. So our first step is to take the Laplace of both sides of the equation. This is just like taking the integral of both sides, the derivative of both sides. This is an integral transform, but we just, as long as we apply it equally to both sides, we keep the equality. So we're going to have the Laplace transform of x prime is going to equal the Laplace transform of negative kx plus bu. Secondary note, k and b are constants here. Simple scalar constants. Let's do the right-hand side first, because in some sense it's easier. So negative k is a constant, Laplace transform is an integral, we can move it inside with constants, and then the transform of x of time becomes its transformed version, what we call big capital X of s, or sometimes it's written as x bar. We're going to stick with capital letters here for the transform version. If you want to think of an analogy from earlier in the course, this is like the f hat of omega. This is our frequency domain. Here we have our time domain. Now we're getting this s domain. All right, plus bu, well, b is a constant, and u is a function of time, so it's going to have a transform as well. We don't know what it is yet because we haven't chosen a control strategy, but whatever it is, we can take its transform. Back on the left-hand side, we just go back to our table for a moment here. The transform of x prime is xs of x minus x of 0. S x of s minus x of 0. And so when we say take the Laplace transform of an equation, a differential equation, this is what we get. Now keep in mind what our goal is. It's to find what x equals. What we're going to get out of this is not quite that, but you'll see something very closely related. We're going to solve for its transform version, the capital X of s. So if we do that, we're going to move a couple of terms around. We're going to move this one to the right-hand side and this term to the left-hand side. So we're going to have s x of s plus k times x of s is equal to positive x naught plus bu of s. Perfect. Now we're going to factor out this x of s here, so we're going to get s plus k. Again, remember s here is our variable. That doesn't look like much going on right here, but s is our variable and k is a constant. So these are slightly different terms going on here. But we have that times x of s, and I'm just going to put the control first, just for style reasons. But otherwise, treat everything else as it was before. And finally, we get x of s is equal to 1 over s plus k times all of bu of s plus x naught. Now, in a more traditional differential equation class, we would go and spend a whole pile of time trying to reverse engineer this and get back to x of t equals. However, we are using instead Python and tools to automate that process for us. What we're going to expect you to do is be able to get to this stage here, take the transform, starting with the equation, and manipulating until you get the solution as a function of s. And then we're going to spend our time analyzing this situation here. What does it mean to have this particular form when we take the Laplace transform? And again, in one of the earlier videos, we talked about this kind of form, and we broke it up into this part here, which we call the transfer function, and then this part here, which we called the control plus the initial conditions. And again, it depends on the initial conditions. It's not equal to it, but basically we have some combination of control and initial conditions here and the transfer function here, and we can separate those and distinguish them very clearly as two parts of the product. So that's all we expect for now. Let's take a look at a slightly more complicated example with the spring mass system, where we're applying some external force to this system here, actually some external force of b times u, and we're going to go through the same process. So we're going to take the Laplace of both sides. And here what do we have? We have k, m, c, and b are all constants. Let's do that up here. And once we do that, I'll write it out longhand once. And Laplace of all of this stuff, negative kx, negative cx prime, plus bu. Again, u is a function of time, it's our control. And we're going to do the left-hand side first this time because this is going to get long and going to fill up some space. So going back to our table of transforms, x double prime gives us an s squared. So every s that you see in a transform like this correlates to one derivative. And then we have these extra ingredients here that come from the initial conditions. And following the pairing, the s's are going down, the derivatives are going up, and this is position and velocity as the starting values that we need to be able to simulate or predict. So we'll keep that in mind. S's are going down, derivatives are going up in this setup. So we're going to have m times the s squared capital X of s. So whatever our solution is, whatever the motion of this system is going to be defined by X of s, transformed. And then our s's are going down, and our derivatives are going up. So I start with no derivatives, then one derivative. I start with one s, then I get 0 s's, and that gives us the transform of the left-hand side. I'm just going to tidy that up a hint. X prime of 0. So then, on the other side, we get something similar to last time. We're going to have negative k transform of x, which is capital X. And here we have a first derivative, so we do get something fairly long here. So we go back to our table. One derivative means s times our unknown x minus the initial condition. 1s times x of s minus our initial condition. And then plus b transformed u of s. Okay, same strategy. We want to then solve for the behavior of the system, x of s, in its transformed state. If we look carefully, we see x is here, and x is here, the x of s's that is. And when we gather all those, we're going to have ms squared x of s plus, by the time we bring this over, plus k x of s and plus a cs x of s. Then if we take the other terms and move them all to the right-hand side, we're going to have a whole gallery of these. We're going to have a negative c times the x naught. In fact, I'm just going to call that x naught just for space reasons. So x of 0, x naught. And we're going to have a plus s x naught and a plus v naught. That would be our x prime of times 0 and plus b times us. Gathering terms again, each of these x of s's is in that term, so I'm going to gather it as well. In fact, I'm going to gather it this way. I'm going to bring the x of s out front and then scratch it out from each of these terms here, just to save again a little bit of space, because then we can get our solution x of s is equal to all of this. I'm going to put it here, and again I'm just going to list the control function first. That tends to be the most relevant for what we're doing. But these other terms also come along for the ride, and my apologies. This should be a positive cx naught, positive sx naught, plus v naught, and we have our bus already. And then over here, we have 1 over ms squared plus cs plus k, simply listing these in decreasing order of our s values, squared, linear, and then constants. And notice when we do that, we get the same structure we've had with our first order differential equation. We have some multiplier, and we have then the control and the initial conditions. So again, here we have our transfer function, and then beside that, or multiplying that, we have our control, and again, not just the initial conditions, but some function of the initial conditions, something related to them. And in some sense, that's the major insight. When we take the Laplace transform of a linear differential equation, the linear is some subtext here we haven't brought up, but it's important. When we do that, what we get is a consistent form of an equation in the S domain. We always end up with this building block function here, and then our control and initial conditions over here. And it's always this transfer function, or this collection of functions of s's, multiplied by these things here. Our next step is to try to interpret that and see what kind of insights we can gain about the system from this form that was not accessible to us in the original form.